Hello and welcome to this Mr. Cold Chemistry video going through the Redox practice test. Question 1a is a titration question. It is important to start by getting a good understanding of what's happening in the question. So here we have a sample. That sample is dissolved in water. Then a portion is taken from that, which is then titrated against dichromate. In this question, we're going to have to work backwards. So you start by working out the moles of dichromate, then the moles of Fe2+ in the 25 centimeter cubed portion, then the moles of Fe2+ in the 250 centimeter cubed portion, which then tells you the moles in the sample, the original sample, and then you can use the MR to work out the mass of iron sulfate. Starting with the moles of dichromate, you can use moles equals concentration times volume. Note that I have divided the volume of 21.3 by 1000 in order to convert our volume to dm cubed, which it needs to be for this equation. Now that we know the number of moles of dichromate, we have to work out the moles of Fe2+ in the 25 centimeter cubed portion. To do this, we have to use the ratio in the equation. However, we are not given the ratio, we are not given the equation. This actually makes the question a little harder than is typical. So we have to work out the equation first. We have to start by writing the half equations for the two different reactions. We know that dichromate is an oxidizing agent, so we know that Fe2+ is going to be oxidized to form Fe3+. Therefore, the equation is Fe2+ goes to form Fe3+ plus E-. As we said before, dichromate is an oxidizing agent, so it must be reduced. You have to know what it's reduced to. So you have to know that dichromate can be reduced to Cr3+. Therefore, the equation is Cr2O72- plus 14H plus 6E- goes to form 2 chromium 3+ plus 7 waters. Note that we have balanced the chromiums by having 2 lots of chromium 3+ on the right hand side. We have balanced the oxygens by having 7 waters on the right hand side. And we balance the hydrogens by adding 14H plus to the left. The electrons are added to balance out the charge. Note that there are 2 Cr3 pluses on the right, so you only need 6 electrons to get the charges to be the same on each side. Now we have to combine the two half equations to create the overall equation. As there are 6 electrons in the dichromate half equation and 1 in the iron 2+ half equation, we need to multiply the iron 2+ equation by 6 and then combine them, cancelling out the electrons. This gives us and tells us that the ratio in the equation is 1 to 6 with respect to dichromate to iron 2+. Now that we have the ratio, multiply the number of moles of dichromate by 6 to get the number of moles of Fe2+ in 25 centimeters cubed. In order to work out the number of moles of Fe2+ in 250 centimeters cubed, we have to work out the sampling ratio. In this case, it's extremely simple. We had 250 centimeters cubed originally and took a 25 centimeter cubed portion. Therefore, we have to multiply the number of moles in 25 centimeters cubed by 10 in order to work out the moles in 250 centimeters cubed. Okay, so now that we have the number of moles in the original sample, work out the MR of hydrated iron sulfate and multiply by the moles, and that will give us the mass. Note that the MR does include the water of crystallization, so note the formula above is FeSO4.7H2O, so your mass does include the water, so your MR includes all of the waters there as well. This should give you an answer of 5.33 grams. Question 1b wants you to suggest the property of the impurity that would result in the calculated mass being too big. Normally, we're used to impurities reducing the amount of something, but in this case, we're getting more of it than we should have. Looking back through the calculations, we need to find an impurity that would result in the dichromate reacting more than if it does if we had a pure iron sulfate heptahydrate. There are a couple of different possible ways to achieve this. The first is that if the MR of the iron sulfate heptahydrate is too small for some reason. This would result in a similar mass of impurity reacting with more dichromate than the pure version does. So, how do we have a smaller MR? Well, the answer is to have an iron sulfate with fewer waters of crystallization. So, for example, rather than having FeSO4.7H2O, you have FeSO4.5H2O. The same mass of pentahydrate would have more moles of iron 2 plus ions than the same mass of iron sulfate heptahydrate. The second way is to have an impurity that is a different substance altogether, but is also a reducing agent. It could be that it is a stronger reducing agent, or it could be that it has a smaller mass. Doesn't really matter which it is, as long as the same mass of the impurity would react with more dichromate than the pure iron sulfate heptahydrate would. So there we have our two possible answers. Firstly, the impurity is iron sulfate with fewer waters of crystallization, or the impurity is something else but is also a reducing agent. The second mark then, for either one of these two explanations, is for equal masses, the impurity would react with more dichromate than the pure version would. Question 2 wants us to determine the highest oxidation state of chlorine in these four examples. It isn't particularly time-consuming to work out the oxidation state of chlorine, so my recommendation would be just to do it for all of the options here. I'll start by just quickly reminding you of the rules. All the oxidation states must add up to the charge of the molecule or the ion. Fluorine always has an oxidation state of -1 unless it's bonded to another fluorine, and oxygen always has an oxidation state of -2 unless it's bonded to another oxygen or to fluorine. There are a few other rules, but in this particular case, they're not important. Okay, starting with A. There are two fluorines, which each one being -1 adds up to -2. So chlorine has to take the oxidation state from -2 to -1, so it must have an oxidation state of +1. Then looking at B, we've got 4 oxygens, which add up to -8. The chlorine has to get the oxidation state from -8 to -1, so it must be +7. We actually don't need to go any further in this question, because the maximum oxidation state on a chlorine is +7, which means B has to be the answer. The reason that +7 is the maximum oxidation state is because chlorine has 7 electrons in its outer shell, and therefore it can't lose more than 7. However, let's just check C and D while we're here. C, chlorine is +4, as it has to get the oxidation state from -4 to 0. And D, chlorine has an oxidation state of +3, because it has to get the oxidation state from -3 to 0. So the answer is B. Question 3 has a series of statements about the equation given. Before I start, I'm going to write the oxidation state of the relevant elements underneath them to make it easier to evaluate the statements. Starting with tin, it is starting at 2+ and ends at 4+. Then, if we look at the chromium, it starts at +6 and ends up at +3. Okay, so looking at the statements, each of the statements are about the agents, so whether something's a reducing agent or an oxidizing agent, and the electrons, whether they're gaining or they're losing electrons. So remember, if something is an oxidizing agent, then it is being reduced, and vice versa. And remember that oxidation is loss of electrons, and reduction is gain. Statement A. Statement A is incorrect because the tin is being oxidized. So it is the reducing agent. It also loses electrons. So A is not correct. Statement B is also incorrect because although it is the reducing agent, it loses electrons. Statement C, chromium is reduced, so it is the oxidizing agent, and it does indeed gain electrons. C is correct. We'll just quickly check D as well. So statement D, chromium is reduced, so it is not the reducing agent. So the answer is C. Question 4 wants you to add hydrogen ions and electrons to balance the equation. In each case, you need to balance the number of hydrogens first and see if 2 are needed on the left. Once you've done that, you can then see if an electron is needed. Okay, so starting with A, there are indeed 2 more hydrogens on the right than there are on the left, so you do need 2 extra hydrogen ions on the left. However, because everything is neutral first, when you add 2 hydrogen ions to it, you are going to need 2 electrons on the left to balance out the charge. So A is not correct. Question B, you have 2 hydrogen atoms on the right, so you need to add 2 H plus ions on the left. Once you do that, you have a charge of 4 plus on the left and 3 plus on the right, so you need to have 1 extra electron on the left. B is the correct answer. C is not correct because you only need 1 extra hydrogen ion on the left, and D is not correct because you would need 2 electrons on the left. So the answer is B. Question 5A1 is just a fact that you should know from GCSE. Oxidation is the loss of electrons. Question 5A2 wants you to work out the oxidation state of nitrogen in 2 species. In NO, there is 1 oxygen, so the nitrogen has to have an oxidation state of +2 to balance out the -2 from the oxygen. In ammonium, there are 4 hydrogen atoms, each with an oxidation state of +1. The nitrogen has to get from +4 to the charge of +1, so it has an oxidation state of -3. In question 5A3, you have to work out which substance is formed from oxidation. You already know the oxidation states of the nitrogen in the reaction, so you know it goes from +4 to -3. This means that the nitrogen is being reduced. The iodide, therefore, must be being oxidized, and the product that is formed from oxidation is I2. Question 5B1 wants you to write the half equation for the formation of chloride ions from chlorine. This is straightforward. Start by balancing the atoms and then add in any electrons needed to balance the charge. Question 5B2 is a little trickier. Start with the sulfur-containing compounds and balance the number of sulfurs first. Next, add in any water molecules to balance the number of oxygen atoms. Then, add in any hydrogen ions to balance out the number of hydrogen atoms on the left. And finally, add in electrons to balance the charge. Don't forget to look at both the sulfate and the hydrogen ions when you're balancing the charge. Question 5B3 wants you to combine the half equations to create the overall equation. This is a relatively simple example of this type of question because the 2 equations both have the same number of electrons already, which means the first step, which is to make sure they both have the same number of electrons, is already done for you. All you have to do then is combine the equations into one larger equation and then take out the electrons. This results in our equation there. To answer question 6a, you have to know that oxidizing agents are reduced and vice versa, and therefore oxidizing agents gain electrons. Question 6b1 asks you to identify the oxidizing and reducing agents in the equation. I would start by writing the oxidation number underneath the sulfur and the silver in both the reactants and the products to determine the oxidation state changes. You can see that sulfur starts at +4, balancing out the 2 2- oxygens, and ends up at +6. Silver starts at +1 and ends at 0. Sulfur was oxidized, making it the reducing agent, whereas silver was reduced, making it the oxidizing agent. Note that in this sort of question, an oxidizing agent and a reducing agent are specific reagents, which means that you can't say that it is the silver and you can't say that it is the sulfur. You have to say it is the Ag+ and it is the SO2. Question 6b2 wants you to write a half equation. Start by writing in the sulfur-containing compounds and balance the number of sulfurs if necessary. Next, we will add in water to balance out the number of oxygen atoms, and then we'll add in hydrogen ions to balance out the number of hydrogen atoms. Finally, we'll add in electrons to balance the charge. Question 6c1 wants you to write another half equation. This one is nice and straightforward. Question 6c2 wants you to determine the oxidation state of chlorine. There are 3 oxygen atoms in the substance, which adds up to -6. The chlorine has to get from -6 to -1, so it must have an oxidation state of +5. 6c3 asks for a half equation. Start by writing out the chlorine-containing compounds and balance the number of chlorines. In this case, no balancing necessary. Next, we're going to add waters to balance out the number of oxygen atoms, and add hydrogen ions to balance out the number of hydrogen atoms. Finally, we're going to add electrons to balance out the charge. The combined equation is achieved by balancing the electrons first. By this, I mean that the number of electrons in each half equation should be the same. We therefore have to multiply everything in the first half equation by 6. Once we have done that, we can combine the equations together and cancel out the electrons to get the final equation. Okay, so question 6D involves a little bit of sleuthing. So you're told in the question that sulfur is moved from the impure ion using magnesium. So it must be a reaction between sulfur and magnesium. The next thing, of course, is to try and work out what we make. Well, we've got a metal and a non-metal, and we know that if they react together, they'll make an ionic salt. So, for example, if we were to have sodium and oxygen, they would make sodium oxide. If we were to have iron and chlorine, you'd make iron chloride. So, sulfur and magnesium, or magnesium and sulfur, put in the magnesium first, gives us magnesium sulfide. The formula of magnesium sulfide is MgS because magnesium ions are 2+ and sulfide ions are 2-. In this case, the oxidizing agent is the substance that is being reduced, which is the substance that is gaining electrons. The sulfur is going from an oxidation state of 0 to an oxidation state of -2, so it is the sulfur. Question 7a is just a regular reaction between a reactive metal and an acid. It is the same reaction that you will have dealt with at GCSE. So the answer is iron plus sulfuric acid goes to form iron sulfate and hydrogen. Question 7b is writing an equation. Honestly, I'm a little surprised that this is only worth 1 mark. Manganate goes from MnO4- to Mn2+. You have to just know this one, I'm afraid. So the equation is iron goes from Fe2+ to Fe3+, so the equation is this. And therefore the combined equation is this. C involves getting your head around the process that took place at the very beginning of the question. So we have a sample of iron which is impure, and it contains impurities of carbon. You have 1.27 grams of this impure iron, which is then reacted with excess dilute sulfuric acid. Now, in this process, nothing's happening to the number of ions. Okay, they start off as iron atoms and then end up as ions, but the number's not changed, so that's quite useful for us. That solution has been made up to 250 centimeters cubed, again, doing nothing to the number of ions. And then a 25 centimeter cubed sample, or I like to use the word portion just to differentiate between the word sample at the beginning. So 25 centimeter cubed portion was taken, and of course that means you've taken 1/10 of the ions present. Then that reacted against potassium manganate and involved that concentration and that volume. So we have to work backwards in this question. So we have to start off by working out the number of moles of potassium manganate. We then have to use the ratio in the equation that we've already just done in order to work out the number of moles of iron 2+ ions in 25 centimeters cubed. Then take the ratio from the sampling method we used, so it's just a 1:10 ratio, so times that by 10 to give us the number of moles of iron 2+ ions in 250 centimeters cubed. And that is the same number of moles as there were iron atoms, or moles of iron, in the original 1.27 gram sample. Convert that to a mass, and then we can work out what percentage that mass is of the 1.27 grams of our impure iron. Step 1 is to work out the moles of manganate. Moles is equal to concentration times volume. Do note, of course, that the volume has to be in dm cubed, which is why I've divided the 19.6 by 1,000. Times by the concentration gives you 4.312 times 10⁻⁴ moles of manganate. Step 2 is to work out the moles of iron 2 plus in 25 centimeters cubed portions. It is a 1:5 ratio of manganate to iron, so multiply the number of moles of manganate by 5, and that gives you your moles of iron 2 plus. Step 3 is to work out the number of moles of Fe2 plus in 250 centimeters cubed. So take the number of moles in 25 centimeters cubed and times it by 10. Step 4 is to work out the mass of iron. Now what we have to acknowledge here is that the number of moles of iron 2 plus is the same as the number of moles of iron. So I've sort of missed out an imaginary step in the middle here where I say moles of iron. Moles of iron are 2.156 times 10 to the minus 2. And therefore to work out the mass of iron, we have to take that value, that number of moles, times it by the MR of 55.8, which gives us our mass of 1.203 grams. Our final step is to work out the percentage mass of carbon in our sample. Now just be careful here, it's easy to fall at the last hurdle because you've stopped paying attention to the fact that the question asks for the percentage mass of carbon, not the percentage mass of iron. So you have to work out the mass of carbon first, which is 1.27 minus 1.203. So that's your mass of carbon. Then divide that by the total mass and times by 100 to turn it into a percentage. That gives you 5.28%. Question 7D wants to know how you would ensure the reliability of the results obtained in this experiment. You would do this by repeating the titration and taking an average of the concordant results. Question E wants you to suggest one way in which the reliability of this analysis could be improved. It's worth pointing out at this point that we're not talking about precision, we're talking about reliability. If we were talking about precision, or we were talking about reducing the amount of error, you'd want to be talking about the volumes that you've taken, or the masses that you've taken. Taking a larger mass would give you a more precise answer, with fewer errors. However, it doesn't ask you how you're going to reduce the error, it asks you how you're going to make sure it's more reliable. You have to then look at what you're actually trying to achieve in the question. In the process, you are trying to work out how much carbon there is in the overall process by taking a small sample. That small sample, of course, is localized. If you took it from the bottom of the container, is it going to be the same as swimming if you took it from the top of the container? Does carbon float? Or does it sink? Does it distribute evenly? Or does it go to the edges? You don't know the answer to these questions, and therefore you should take samples from a variety of different places within the process. Okay, that brings us to the end of this walkthrough. If you have any questions, please leave a comment, and if you found the video useful, press the like.